Hello students. So our goal today is to introduce another law involving non-right triangles, which is similar in some ways to the law of sines, but it'll give us different kinds of information. And this rule, instead of being inspired by the idea of SOHCAHTOA, will be just inspired by thinking about how the Pythagorean identity changes if you try to apply it to a triangle that's not a right triangle. So let's just remember what the Pythagorean identity says for a right triangle. If this triangle is a right triangle, then the Pythagorean tells you that a squared plus b squared is equal to c squared. Well, what if I take that right angle and I start squeezing it a little bit? If it's now not a right triangle, but this side length is still a, that side length is still b, then this side length is going to be a little bit shorter. Right? It should start getting squeezed to something a little bit shorter than what it is in this picture. So that means that as this angle changes, this side length should change. There should be some formula that tells you what this side length is if you know this angle and the two sides at which it meets. So let's try to figure it out. So let's start with this. Here is, right here, a picture of some triangle which has a side length, and an angle. I would like to find a formula for this opposite side length in terms of a, b, and theta. And that's too hard to do all at once. Instead, we'll do it by breaking up this picture into pieces. So I see right here a right triangle. If I drop a perpendicular from this point to that line, then that will break this triangle in question up into two smaller right triangles. So let's study that. I'm not actually interested in the side length h, the height of the triangle, or a0 and a1, what dropping that height does to that bottom length, but I'll need to understand them in order to get a hold of the side length c, the thing that I'm really interested in. So let's just look at this and see what we can do. So this yellow triangle is a right triangle. I can use the fact that that is a right triangle to figure out things. So I'm interested in formulas which involve theta and b. So I should think that I know theta and b. I should try to figure out everything else. Well, I can figure out h in terms of theta and b. H is the side opposite theta, b is the hypotenuse. So by SOHCAHTOA, sine theta is equal to h over b. Solving for h, we get h is equal to b multiplied by the sine of theta. Cool, cool. Similarly, I should be able to find the side length a0, because cosine of theta will be adjacent over hypotenuse. There's the adjacent, there's the hypotenuse, so the cosine of theta is a0 divided by b. Solving that for a0, I get a0 is equal to b multiplied by cosine theta. I know what the base of the triangle is. The base of this triangle is equal to a1. So that means that a0 plus a1 should be a, the base of the whole triangle. So what is a1? You can solve for a1. a1 is a minus a0, but I know what a0 is. It's b times the cosine of theta. So a1 is equal to a minus b times the cosine of theta. And now you should see how what we're about to do. So I'm interested in that side length c. But this triangle is also a right triangle. I know the base of that right triangle. I know the height of that right triangle, so I can figure out the hypotenuse. According to the Pythagorean identity, c squared is equal to a1 squared plus h squared. Nice. But I also know what a1 and h are, so let's use that. So a1 is a minus b cosine theta plus h squared, I'm going to put the square there, plus b sine theta, because that's h squared. So on the one hand, this gives us the formula we wanted. There's a formula that will tell us the side length c in terms of the side lengths a and b and theta. Now, that formula is obviously more complicated than it needs to be. Let's simplify it. How will we simplify it? Well, let's FOIL everything out. Let's use the fact that squaring things isn't so hard to do. and we'll see what simplifies. So let's simplify. C squared is equal to, first we FOIL out this bit, a squared minus 2ab cosine theta plus b squared cosine squared theta. So that's just by FOILing out the first term, plus b times the sine of theta quantity squared is the same thing as b squared sine squared theta. So, again, there's another formula. It doesn't look that much simpler than what we had before. I think that we can simplify it more now because there are two terms that look like they should have something to say to each other. Check out those two terms. So let's combine those two terms and maybe a factor of b squared out. So this is the same thing as a squared minus 2ab cosine theta plus factor out the b squared for the sake of color, yeah, that's color code, cosine squared theta plus sine squared theta. So what have I done? I've taken these two terms, I've factored a b squared out of them. Why would I do that? Well, I know what cosine squared plus sine squared is. By the Pythagorean identity, that is equal to a squared minus 2ab cosine theta plus b squared times 1. That formula is the law of cosines. The law of cosines says if a, b, and c are edges of a triangle, and c is the side length opposite theta, then this formula is true. And I'll just rewrite it so that a squared and b squared come first and then this term afterwards. C squared is equal to a squared plus b squared minus 2ab cosine theta. And so if you look at this, you see one term, I like that color, that looks like the result of the Pythagorean identity. Of course, we can't use the Pythagorean identity. This is not a right triangle, so there's some error term. So that second term somehow tells you how far the Pythagorean identity is from being correct on this triangle, which of course you don't expect it to be correct because it's not a right triangle. So, nice. So we now have the law of cosines. Let's use the law of cosines. Let's start by even just writing down the law of cosines again. The law of cosines says that if you draw some triangle, side length A, side length B, side length theta, side length C, then c squared, the side length opposite theta, is equal to a squared plus b squared minus 2ab cosine theta. So let's use this. Let's use this to make a computation. So here's a triangle. It's got a side length of 3, a side length of 5, an angle of pi over 3. This is obviously not a triangle that's drawn to any sort of scale. Let's try to figure out how long that unknown side length c is. So I know two angles, two sides and the angle at which they meet. Those are all of the variables on this side of the Pythagorean, not the Pythagorean identity, of the law of cosines. So we can use the law of cosines. The law of cosines will say that c squared is equal to 5 squared plus 3 squared minus 2 times 5 times 3 times the cosine of pi over 3. Alright, so on the one hand there's an answer, but I know what all of those things are, so I should simplify. See, 5 squared is 25, plus 3 squared is 9, minus 2 times 5 is 10, times 3 is 30, times, what's the cosine of pi over 3? Grab your unit circle, open it up, that's 1/2. So, c squared is equal to 25 plus 9 is 34, minus 30 times 1/2 is 15, equals 19. So c squared is equal to 19, so the side length c itself is equal to the square root of 19. Right? It can't be negative the square root of 19 because it's a side length in a triangle. It can't be negative. I'll stop this video soon. Let me give you an overview of what else is in these notes. So, right now we have two laws we can use. We can use the law of sines and the law of cosines if we want to solve a triangle. So I want to give you an idea of how to solve different triangles, where solve means find all of the information about the triangle, given limited information. So we'll go through some cases and see how they walk. We'll do an explicit example of a side-side-side triangle. And then we'll do a few applications. Nice. So this video is over. I'll see you in the next one.